Well, welcome back. Dr. P here, and we'll continue our discussion of organic chemistry. And today we're going to move on into chapter 2, and we're going to start looking at polar covalent bonds and drawing resonance structures. Actually, I think I'll have a separate lecture for resonance structures, just it can take a while. All right, so let me go ahead and share my screen here. And hopefully when you watch this, you'll actually see me pop up in the corner, because I always feel like it's nice to have a sort of person that you're looking at. You can see facial expressions and stuff instead of just some disembodied voice off camera. Anyway, let's take a look at polar covalent bonds. Now, these will enter into how things react. They'll enter into some of the properties of acids and bases, and also enter into solubility, which we'll see in lab. So let's look at an example here. Let's look at acetone. So acetone, as you may remember from previous lectures, is a good solvent. I'm going to say a good organic solvent. It dissolves lots of nonpolar stuff. It's also miscible in water. And miscible just means soluble for liquids. Now, if we take a closer look at our acetone here, we see that we have a C double bond O, which is a carbonyl functional group. Sorry about that. All right. Now, carbon oxygen double bonds like this, actually any carbon oxygen bond, even single bonds, do not have the electrons evenly distributed. They are what we call polar. We have a partial negative charge on the oxygen and a partial positive charge. So our delta minus and our delta plus are partial charges. And what this gives us is a polar covalent bond. So we'll say CO bond is polar covalent. So it is a polar covalent bond. So to represent that, we draw this arrow where one end is kind of a plus. So that's the end that's more on the positive side, and arrows pointing towards the side with more electron density. Because of the way acetone looks, because of its shape, its geometry, one side ends up being more positive. That is, one side of the molecule is more positive than the other side. And so we have a net dipole moment. We draw that the same way that we would draw the polar covalent bond with that arrow with the plus sign at one end, only we make it bigger for the whole molecule. Now, acetone is very polar, and you don't need to know these numbers, but I thought I would provide them anyway.
And in this case, the dipole moment, or mu, that's the Greek letter mu, for acetone is 2.91 debye. I don't remember what a debye is in the base SI units, so I just understand that more debye is more polar. For water, we have, for gaseous water, we have a dipole moment of 1.86 debye. And then for liquid water, we have a dipole moment of 2.6 debye. So that's interesting that acetone is more polar, technically speaking, than water is. Usually we think of water as being the ultimate polar solvent, but it turns out that is not exactly true. It works as a superpolar solvent, and we'll see why that is a little bit later. But first, I want to talk a little bit about how these polar covalent bonds arise. And the property that we're interested in is called electronegativity. Electronegativity is the tendency of an atom in a covalent bond to pull electron density toward itself. Let me read that again. Electronegativity is the tendency of an atom in a covalent bond to pull electron density toward itself. And we can assign some quantitative values to electronegativities. And these are on the Pauling electronegativity scale, named after Linus Pauling. So we've got H, hydrogen, lithium, beryllium, sodium, magnesium. And we'll skip over here. Boron, aluminum, carbon, silicon, nitrogen, phosphorus, oxygen, sulfur, fluorine, chlorine, and bromine. Now, fluorine is the most electronegative element with a value of 4.0. And we could do this for the whole periodic table. The general trend is electronegativity increases going to the right on the periodic table and going up. So chlorine, for example, has an electronegativity of 3.0, bromine is 2.8, oxygen is 3.5, nitrogen 3.0, carbon 2.5. I'm just going to fill these in here. You can find these in the text. And if not, I can find a figure for you. Of course, I will be scanning in these notes so you can have your own copy here. And what we're looking for is a difference in electronegativities. So just some examples here. Let's say we have HF, hydrogen fluoride. Fluorine is more electronegative than hydrogen. Our electronegativity difference is 1.9 in this case. So we'll have a delta plus partial positive charge on the less electronegative end, or atom, and a delta minus partial negative charge on the more electronegative end. That gives us a net, that gives us a polar covalent bond and also overall a net dipole. Now, we can look at some other examples here. Let's look at carbon dioxide. Here, our electron difference, our electronegativity difference is 1.0, which is still significant. So we would have a delta minus where the oxygens are and a delta plus where the carbon is. So what happens is our polar covalent bonds essentially offset each other. So this guy is non-polar. And we can say that the polar covalent bonds offset. A case of if we have really, really different electronegativities, like for example, lithium fluoride, our difference here is 3.0, which is really ionic. It's not a covalent bond. So we're better off drawing this as lithium plus and then a fluoride ion, F minus. So long story short, polar covalent bonds are one thing that's necessary to get polar molecules, but they have to be combined with the correct geometry. And we'll look at more examples of this later. So again, just to reiterate, polar covalent bonds combined with the correct geometry of our molecule give rise to polar molecules. So let's revisit acetone. I'm actually going to draw a little bit more of the Lewis structure here. I'm still indicating how it is trigonal planar, of course, but now we can see all of the hydrogens. And again, this is polar. And we can compare that to water, delta minus, and delta plus on the hydrogens. But because water is bent, we have a net dipole moment as well. So water is also polar. Now, water can do something interesting that acetone can't do. And the reason why we say water is such a great polar solvent is that it can form hydrogen bonds. So if I draw a couple of water molecules here, and these dashes represent the hydrogen bond. So we have a hydrogen atom that is quote unquote shared between two electronegative second period or second row elements. So it only happens with nitrogen, oxygen, or fluorine. So what that means is now our acetone, if I redraw the structure here, our acetone is a hydrogen bond acceptor. That is a molecule of water or alcohol or something that has a hydrogen attached to an oxygen in this case. It can be donated and be accepted by the oxygen in acetone. However, these hydrogens attached to the carbons cannot form hydrogen bonds. And so even though acetone is polar, it doesn't do as good a job of dissolving polar things that have hydrogens available for hydrogen bonding. So it's not, we say it's not as good a polar solvent as water is. Okay, well, I think that is enough for now. I'm going to stop sharing, and in the next video, I'll talk about resonance structures, and then after that, we can talk about acids and bases. So until next time, stay safe out there.